Alright, today we'll talk about gateways, especially IoT gateways for Industry 4.0. Okay, let's look what's happening here. What we are really talking about here is the industrial Internet of Things or IoT and especially the gateway. Think of the gateway as a point where the operational world and the IT world finally agree to talk to each other. On one side, you have operational technology, PLCs, sensors, drives, machines that were never designed to speak aloud. On the other side, you have IT systems, analytics platforms, databases, dashboards. The gateway sits right in between and makes that conversion possible reliably and safely. Okay, now why does this matter? Because modern manufacturing depends on continuous data flow. Legacy machines generate valuable signals, temperatures, vibrations, counters, states, but by themselves they are isolated. The gateway pulls that data out, normalizes it, and pushes upstream so it can actually be used. Okay, and here's the big shift. Traditional automation was closed and local. You programmed a PLC, it controlled a machine, end of story. With IoT gateways, factories become connected systems, and data is collected in real time, processed at edge, and then forward for analytics and decision making. This is how you get predictive maintenance, adaptive production lines, and fast feedback loops. Every machine becomes a data producer, not just a mechanical asset. Okay, so here, Industry 4.0 is basically the fusion of physical systems with digital systems. Cyber physical systems, cloud computing, IoT, analytics, they all come together. But none of that works if you can't get data out of the plant securely and consistently. That's why gateways are so central. They are the enablers that make Industry 4.0 practical instead of theoretical. Okay, now what does a gateway actually do in practice? We'll talk about this. First, protocol translation. Machines speak Modbus, Profinet, OPC, UA. IT systems expect MQTT, HTTP, WebSockets, and the gateway converts between them so systems don't need to be rewritten. This is huge because replacing equipment is expensive. Next comes data aggregation. Instead of sending raw signals from thousands of sensors directly to the cloud, the gateway collects, cleans, and aggregates them locally. Why do we do that? Because bandwidth, cost, money, and latency matters. You send only what's useful. Security is another core function. The gateway becomes a controlled boundary. Firewalls, VPN, tunnels, device authentication, network segmentation. You never expose the plant network directly to the internet. The gateway absorbs that complexity. Then there's edge computing. This is where logic runs locally. Analytics, control logic, even machine learning inference can execute right at the gateway. If the cloud connection drops, the system still works. And that's not optional in industrial environments. And network bridging is about connecting isolated OT networks to IT networks without breaking safety rules. And legacy integration is required here. Decades old machines suddenly participate in modern systems without being replaced. Okay, and legacy integration part here. And let's look use cases like that here. Once we have that foundation, the use cases start to make sense. So Predictive maintenance comes from continuously monitoring vibration, temperature, and acoustic signals. Models running at the edge detect failure patterns early, cutting unplanned downtime dramatically. Production optimization uses real-time OE, that's overall equipment effectiveness, to balance lines and improve throughput. Quality control integrates vision systems and sensors for automated inspection and SPC, statistical process control. Energy management here becomes possible because energy data is visible in real time. Supply chain integration works because inventory and material movements are tracked instantly. Digital twins synchronize physical assets with software models. Worker safety improves through environmental monitoring and proximity detection. And track and trace systems give you full product genealogy, which is important in regulated industries. Okay, and what are the types here? Now, not all gateways are the same. Edge IIoT gateways live close to the missions. They focus on field-level data acquisition and local processing. They support multiple industrial protocols. They are rugged and they mount directly in control cabinets. Okay, and industrial edge servers operate at the plant level. These are more powerful systems with server class CPUs, large memory, fast storage, and sometimes GPUs. They aggregate data from many gateways and run heavier NTX or containerized workloads. And what is next? Here, protocol gateways here specialize in one thing. What's that? Fast, deterministic protocol conversion. They are compact, low latency, and designed for real-time control paths. So finally here, wireless IoT gateways focus on connectivity. They connect wireless sensors, mobile assets, and remote deployment using Wi-Fi, Bluetooth, LoRaWAN, and cellular networks like 4G, LTE, and 5G. Okay, let's continue. Now, we'll walk through the architecture. Yes, now perfect. Okay. On the left, you have the field device layer. PLCs like Siemens S7 or Allen Bradley controllers, sensors measuring temperature and vibration, drives controlling motors, and robots performing physical tasks. So all of that feeds into the IIoT gateway layer here. Inside the gateway, you start with the hardware platforms, typically ARM Cortex A72 or Intel Atom CPUs, enough RAM and SSD storage, and industrial I/O interfaces. And here on top of that runs the operating systems, usually Linux, Ubuntu, Debian, or Yocto, often with real-time kernel support and container runtimes. So then come the protocol connectors here. This is where Modbus RTU/TCP, OPC UA, Profinet, Ethernet IP, MQTT, HTTP, CoAP, MQP, and WebSockets are handled. Above that is the edge processing engine here, data filtering, aggregation, time series databases like InfluxDB, NTX, and ML Inference all live here. Security, another important thing that wraps the entire stack, TLS/SSL. Here, encryption, X.509 certificates, firewalls, VPNs like OpenVPN, or IPsec, SecureBot, and TPM 2.0. And device management handles remote configuration over the air updates, monitoring, logging, and diagnostics. On the right side, data flows into cloud and IT systems. IoT platforms like AWS IoT or Azure IoT, visualization tools like Grafana, SCADA systems, and enterprise systems like ERP, MES, and CMMS. Okay, we can continue. Yes, now to support all of this, the hardware matters. CPUs range from ARM Cortex A53 and A72, Intel Atom and AMD Ryzen embedded. Clock speeds sit roughly between 1.5 GHz and 3.2 GHz with multiple cores and 64-bit architectures. Okay, and memory typically ranges from 4 GB up to 64 GB of DDR4, sometimes with ECC, and storage uses eMMC, M.2 SSDs, or NVMe size based on buffering needs. Okay, and here network connectivity includes multiple gigabit Ethernet ports, industrial Ethernet support, Wi-Fi, Bluetooth, cellular, and even LoRaWAN. Serial and I/O interfaces handle like that. RS-232, RS-485 digital I/O, analog signals like 0 to 10 volts and 4 to 20 milliamps, USB and CAN bus. Okay, and power and environmental specs are industrial grade. Wide DC input range, power out Ethernet plus operating temperatures from -40 degrees Celsius to +70 degrees Celsius, vibration and shock resistance, and high ingress protection ratings. And mechanically, these systems are rugged. Aluminum or steel enclosures, thin rail mounting, wall or rack options, and certifications like CE, FCC, UL, IEC, and ATEX or for hazardous locations. Okay, we are continue. Now we will move from hardware into software because this is where gateways really start to behave like systems instead of boxes. Okay, modern IIoT gateways run a layered software stack, and almost everything here is Linux based. That choice is very intentional. Linux gives you stability, hardware support, and control over timing, which matters when machines expect predictable responses. In many deployments, you will see Ubuntu Core, Debian, or Yocto-based custom Linux. Sometimes real-time kernel patches are applied so the operating system can meet deterministic time requirements instead of behaving like a general-purpose server. Okay, and yes, what can I say here? As on top of the operating systems sits the container runtime, and this is usually Docker, Container, or Podman. Why containers? Because gateways run multiple services at once. Protocol handles databases, analytics, pipelines, and cloud connectors all need to coexist without stepping on each other. Containers isolate those components and make updates much safer. If one service fails, it doesn't take the entire gateway down. Now, once you have containers, orchestration becomes the next question. And for gateways, this is usually lightweight Kubernetes distributions like K3s or Micro K8s. And these manage multi-container workloads, handle restarts, and scale services when needed. This is especially important when you manage hundreds or thousands of gateways remotely. Then comes the edge runtime layer. Platforms like Azure IoT Edge or AWS IoT Greengrass provide a structured way to deploy, monitor, and update workloads at the edge. Open source alternatives like EdgeX, Foundry, and KubeEdge do the same thing without locking you into a single cloud provider. The key idea here is lifecycle management. You don't manually log into gateways to update software. You push changes centrally. Okay, and data has to live somewhere locally, which is where time series databases come in. InfluxDB, TimescaleDB, or QSDB are optimized for high-frequency sensor data. These databases store measurements efficiently and allow fast queries for recent history, which is critical for edge analytics and buffering when connectivity drops. Messaging is handled by brokers. Mosquito speaks MQTT, RabbitMQ handles AMQP, and Kafka manages high-throughput event streams. And these brokers decouple producers from consumers. The sensors publish data, analytics subscribe to it, clouds connectors forward it. No tight coupling, no fragile pipelines. And protocol stacks are another essential layer. Libraries like Leap Modbus, Open 62541 for OPC UA, and PyCom3 for Ethernet IP translate raw device communication into structured data and rest of the system can understand. And analytics engines sits on top. Node-RED allows flow-based logic for quick integrations. Apache Spark handles batch processing when data volumes grow. Custom Python or Go services implement business-specific logic, and this is where raw signals turn into insights. Okay, to make this concrete, we will look at real hardware platforms that run these stacks. The Advantech Uno 2483G is a high-performance industrial gateway. It uses an Intel Celeron N3350 dual-core processor running at 2.4 GHz with 8 GB of RAM and solid-state storage. It offers multiple gigabit Ethernet ports, USB interfaces, serial COM ports, and digital I/O, and it operates from -40 degrees Celsius to +70 degrees Celsius and mounts on a DIN rail, which tells you exactly where it's meant to live. And Siemens Simatic IPC227E sits closer to edge computing than simple data acquisition. It runs an Intel Atom X5 E3940 quad-core processor at 1.8 GHz with more storage and real-time capable Ethernet ports supporting TCN, time-sensitive networking. And fanless design and IP65 protection on the front panel make it suitable for harsh environments. And the Dell Edge Gateway 5200 is more enterprise-oriented. It supports Wi-Fi, Bluetooth, LTE, multiple USB ports, and both Ubuntu and Windows IoT. This kind of gateway often sits at the boundary between OT and IT, aggregating data from multiple sources. At the smaller end, the Moxa UC8112A METLX uses an ARM Cortex A8 processor at 1 GHz with limited RAM and storage. This type of gateway is ideal for compact deployments where power consumption and size matter more than raw performance. Okay, section 2 is done. Let's continue. Alright. Let's talk about protocols, because gateways exist largely to handle protocol diversity. Now, in industrial automation, Modbus RTU and Modbus TCP are everywhere. They use a master-slave model and are simple, reliable, and widely supported. So, OPC UA is different. It's a unified architecture that combines communication with information modeling. Instead of just reading registers, you browse structured data models. It's secure, platform independent, and increasingly common in modern systems. Profinet, on the other hand, it is a real-time industrial Ethernet protocol used heavily in factory automation, especially with CMS equipment. And EtherCAT pushes performance even further, achieving ultra-low jitter measured in sub-microseconds, which is why it's used in motion control. And here, Ethernet IP is common in North American manufacturing, particularly with Rockwell Automation Systems. Profibus is an older field bus that's still widely deployed, and BACnet is common building automation, especially HVAC, and DNP3 is used in utilities and critical infrastructure. And on the cloud side, protocols look very different. Now, MQTT is lightweight, publish, subscribe based, and extremely efficient for constrained networks. CoreApp is designed for resource-limited devices and runs over UDP. HTTP REST is universally supported and easy to integrate but heavier. AMQP supports enterprise-grade messaging with delivery guarantees. And here, wireless protocols extend the picture. LoRaWAN enables long-range, low-power communication for sensor networks. Zigbee supports mesh network for industrial sensors. BLE Bluetooth Low Energy handles short-range connectivity and asset tracking. And Spark Plug B builds on MQTT to standardize payloads for industrial data. Okay, and another diagram, load diagram. Can you see? Yes. Let me align it. Okay. Now, on the left, field devices generate data, right? A PLC like a CMS S7 1200 speaks Profinet. A temperature sensor communicates over Modbus RTU, and a variable drive uses Modbus TCP as SCADA systems exposes data via OPC UA. Okay, and that raw data enters the protocol converter layer. A Profinet parser decodes GSD or GSDML files. A Modbus handler bridges RTU and TSP, and UPC UA client subscribes and browser nodes. At this point, data is still device specific. Next comes gateway processing. Data normalization, standardize types and units. Tag mapping applies consistent naming conventions so data makes sense across systems. Data filtering removes noise and rate limits updates. Edge analytics aggregate values and perform calculations. Local storage buffers data using a time series database, so nothing is lost during outages. From there, data moves into cloud protocol handlers. An MQTT publisher sends messages with specific quality of service levels. HTTP REST APIs push JSON payloads. AMQP clients integrate with enterprise messaging systems. And Kafka produces stream events at scale. OPC UA servers expose data back to SCADA when needed. and cloud services, that's a service. You know, AWS IoT Core, Azure IoT Hub, Google Cloud IoT, or custom platforms consume and process it. Latency at the edge is typically 10 to 100 milliseconds, while round-trip cloud latency sits closer to 200 to 500 milliseconds. Okay, I think we can continue. Now, real implementation example here. Now, I want you to think of this as something you could actually deploy on a shop floor. Okay, here our file name. We start by pulling in the basics. Time and JSON are here for scheduling and payload formatting. Then you see Pi Modbus, which gives us a Modbus serial client for RTU communication that tells you immediately we are talking to a serial device over RS485, not Internet. The Indian import controls byte order, which matters a lot with industrial devices. If you get this wrong, your numbers look fine synthetically but are completely wrong physically. And binary payload decoder is what turns raw Modbus registers into meaningful values. On the MQTT side, we use PAHO MQTT client, which is the standard Python client. Logging is added because gateways run unattended. When something breaks at 3 in the morning, logs are what save you. Right after that, logging is configured at info level here. This is a deliberate choice. Debug is too noisy for production, error alone is not enough, and info gives you lifecycle visibility without drowning the system. Then we define the Modbus MQTT gateway class. This is the core abstraction. Everything the gateway does lives here. Now, inside the constructor, we initialize two words. What's happening? First, Modbus. The Modbus serial client here is configured for RTU mode. The port might be something like /TTY USB0, and baud rate, parity, stop bits, byte size, and timeout all come from configuration. That's important. Gateways should never hardcode device parameters. Different sensors, same gateway, different serial settings. Then we initialize the MQTT client. The client ID comes from configuration, so multiple gateways can coexist without collisions. And we immediately attach callbacks for here, on connect and on disconnect. Okay. MQTT is asynchronous by nature, so you always need feedback about connection state. Next, we store configuration locally, broker address, broker port, topic prefix, device definitions, and polling interval. At this point, the gateway knows what to talk to, where to publish, and how often to do it. Okay. And now, look at the on MQTT connect function. If the return code is 0, the connection succeeded. Anything else means failure. We log both cases explicitly. The disconnect handler logs warnings instead of errors. Why? Because disconnects happen. Networks blip. What matters is that the system recovers. Okay. The connect method ties everything together. First, we try to connect to the Modbus network. If that fails, we stop immediately. There's no point publishing empty data. Then we connect to the MQTT broker and start the network loop. So here loop start spins a background thread. So publishing doesn't block Modbus polling. That separation is essential for timing stability. And let's move to the read Modbus data function, and this is where raw electrical signals turn into numbers. We read holding register starting at a given address for a given count from a specific unit ID, and if the result signals an error, we log it and return none. Returning none is a design choice. It lets the calling logic decide what to do next. And if the read succeeds, we decode the registers. The binary payload decoder is configured with big endian byte order and word order. And here, okay, now endian big means most significant byte first. These must match the device documentation. Then we branch based on data type. Float 32 means 32-bit floating point number. Pronounced float 32, int 16 is a signed 16-bit integer, and uint 16 is an unsigned 16-bit integer. It's 32 is a signed 32-bit integer. If none of those match, we fall back to the raw register value. And this flexibility lets one gateway support many device types without rewriting code. Okay, next is publish to MQTT. First, we construct the topic. It follows the hierarchical structure: topic, prefix, device name, parameter name. This makes subscriptions predictable and scalable. Then, we build the payload. Okay, look at that. The timestamp is in milliseconds since epoch. That's int of time.time times 1000 pronounced time.time multiplied by 1000, and value holds the measurement. Quality is marked good and source identifies the gateway, and this structure aligns with Spark plug B conventions, which is why downstream systems understand it easily. Okay, and publishing uses QoS 1, quality of service 1, that guarantees delivery at least once. Return is set to false, so all data doesn't linger on the broker. Yes, we can continue. Now we get to the run method. This is the heartbeat of the gateway. That's important. We log startup, then enter an infinite loop. Each cycle starts by generating a timestamp. Then we iterate our configured devices. For each device, we extract its ID and name. Inside that, we iterate our parameters. Each parameter defines a Modbus address, register count, and data type. And we call read Modbus data. If the value is not none, we immediately publish it. This design keeps acquisition and publishing tightly coupled, which simplifies debugging. After all devices are processed, we sleep for the polling interval. That interval is in seconds and control system load and data rate. And the loop has two exception handlers. Keyboard interrupt allows clean shutdown during development. A generic exception handler logs errors and sleeps briefly before retrieving. This prevents tight failure loops that can overwhelm the system. Okay, and look at that. When the loop exists, disconnect is called. We close the Modbus client, stop the MQTT loop, disconnect from the broker, and log shutdown. Clean exits matter, especially when gateways restart automatically. And look at the configuration example here. Modbus settings define serial port, baud rate, parity, stop bits, byte size, timeout, and polling interval. Devices are defined declaratively. Each device has an ID and a name and a list of parameters. Each parameter has a name, address, register count, and type. MQTT configuration defines broker address, port, client ID, and topic prefix. At the very bottom, we instantiate the gateway, connect it, and run it. Let's switch gears and look at OPC UA. This is a different style of gateway interaction, and at the top we import client and UA from the OPCUA library. This immediately tells you we are dealing with a rich information model, not just registers. And look at our class. In the constructor, we store the server URL, namespace, index, and placeholders for subscriptions. Namespace index defaults to, which is common for user-defined nodes, but we keep it configurable. And here connect method that optionally sets username and password. UPC UA supports multiple security modes, and this shows how authentication fits in. There is also commented security policy line. In production, this is where certificates and encryption are configured. After connecting, we fetch the namespace array and log it. That step is important because OPC UA nodes are namespaced, and you need to know which index corresponds to your data model. Now, browsing nodes is how you explore an OPC UA server. If no node ID is provided, we start the objects node. Otherwise, we browse from a specific node. For each child, we log its browse name, and this is how you discover what data is available before hardcoding node IDs. And reading a variable is simple. We get the node by its string ID, call get value, and log the value along with its data type. The data type comes back as a variant type, which tells you how to interpret the value. And writing is similar, but requires wrapping the value in a data value and the variant. That ensures the server understands both the value and its type. If the write succeeds, we log success, otherwise we return false. Okay, and here subscriptions are where OPC UA shines. We define a sub-handler class with a data change notification callback. Whenever the server detects a change, this callback fires. We then create a subscription with a publishing interval and subscribe to each node ID in the list. Okay, and this shifts the model from polling to event-driven updates. Instead of asking for data every second, the server pushes updates when values change. Yes, and disconnecting delays subscription and closes the client cleanly. And another example, the examples ties it together. We connect, browse nodes, read temperature and pressure, then subscribe to changes for temperature, pressure, and flow rate. A loop keeps the program alive until interrupted. Okay, that page is done. Now step back and look at the ecosystem view. This is the software stack that surrounds gateways like the ones we just walked through. So Node-RED sits in the application layer and provides flow-based integration. It's often used to glue protocols together quickly without writing custom code. InfluxDB is the time series database optimized for sensor data. high write throughput and retention policies make it ideal for storing telemetry. Grafana sits on top as a visualization layer. It pulls from InfluxDB and other sources to create dashboards, alerts, and operational views. Look at that. Mosquito acts as the MQTT broker. It's lightweight, supports multiple protocol versions, and fits well on edge devices. And Telegraph collects metrics and pushes them into databases or brokers. It shines in heterogeneous environments where many protocols coexist. Docker provides packaging and deployment consistency. Gateways benefit heavily from containerization because updates and rollbacks become predictable. So here we have another stack architecture, and look at this. This diagram shows how everything fits together. At the bottom, hardware and operating system provide foundation. Okay, and on top of that, data persistence layer. Uh, Here, data persistence stores measurements and configuration. Message broker handle event streaming. Application layers process, aggregate, and enrich data. Visualization and interface layers expose insights to users and systems. Okay, data flows both ways. Dashboards read data, control systems write set points, and gateways translate protocols at the edge.